Hello, and welcome to Math with Mr. Bill. I'm Bill Anderson, and today we're going to be talking about problems involving implicit differentiation. Please feel free to leave any questions in the comments, and go ahead and leave any problems that you would like to see down there as well. So today we're working on a couple of word problems, and here's the second one. Air is being transferred from a spherical balloon into a cubical balloon at a rate of 4 cubic feet per minute. What is the change in the total surface area of both balloons when the radius of the sphere is 2 feet and the edge of the cube is 3 feet? So, beyond the absurdity of having a cubical balloon, this is kind of an interesting question. We want to find the total change in the surface area when one is getting bigger and the other is getting smaller. So let's go ahead and draw out here a sphere and a cube. And let's go ahead and give labels to these. So we have here our sphere. The sphere has a radius, call that r. And then we have a cube, and all the side lengths of a cube are the same, and we'll call that s. Now what else do we know? We know that at the time that we're fixing our snapshot here, that the radius of the sphere is 2 feet, and the side length of the sphere is 3 feet. And we also know the change in volume. So we're going to say that air from the sphere is going to be pumped into air into the cube. And so we're going to take air from the sphere and send it into the cube. And so the change in volume of the sphere with respect to time will be -4 cubic feet per minute. And then the change in volume of the cube is going to be +4 cubic feet per minute. Okay, so when we want to talk about things that change and use this thing called implicit differentiation, we need to come up with formulas that have quantities that change. Specifically, in this case, we're going to be talking about the volumes of these two shapes. And we're also going to be talking about the surface area of these two shapes. Both of those are changing with respect to time. And so if you think about the sphere volume decreasing, that surface area is also going to decrease. And likewise with the cube. So let's find the volumes of both of those shapes. So the volume of a sphere is 4/3 pi r cubed. And the volume of a cube is equal to the side length cubed. Okay, so looking at the volumes of each of these, we notice that since the volume is changing with respect to time, that means that the radius is also going to change with respect to time. So I can take the time derivative of both equations. Let's do that with the sphere first. So the derivative of the volume equation, take d dt of that, and we get the derivative of the volume of a sphere with respect to time is equal to the derivative with respect to time of 4/3 pi r cubed. Now the 4/3 pi can come outside of the derivative since it's just a coefficient. And then what we're left to take the derivative of is r cubed. So when we take the derivative of r cubed, we're going to get 3r squared, like normal. But because we're taking the derivative with respect to time, and radius is changing with respect to time, then we have to chain on this derivative, dr dt, because we have to use the chain rule because we're not taking the derivative with respect to r, we're changing it with respect to time. Okay, so now looking at this equation here, well, we know what the change of the volume of the sphere is with respect to time. That's -4, and that's going to be equal to 4/3 pi times 3 times the radius squared. So the radius of the sphere right now is 2. But what we don't know is dr dt. We can certainly get a number for it now since we have everything but that. So solving for dr dt, I'm going to take -4 and divide it by pi times 3 times 2 squared, and then multiply everything by 3/4, so the reciprocal of 4/3. So dr dt is going to be -1 over 4 pi. You can see the 3's and the 4's cancel. Okay, so now that's a thing. That's something that we've got. Okay, may or may not be useful. Or it will be useful, but unless we look through the entire problem, it may not be quite so clear as to what we're going to be able to do with it. But we do have it now. Let's go back up and let's do the same thing with the volume of the cube. Since it's just one variable, or since it's a fairly straightforward equation, it should go pretty quickly. So again, we'll take the time derivative of both sides. So d dt of the volume of a cube. So we have dv dt is equal to the derivative of s cubed with respect to time. So you take the derivative like normal, 3s squared, but then because s is not t, and we're taking the derivative with respect to t, s is changing, then we take the derivative of s with respect to time. So we know the change in the volume of the cube. That's 4. And we know the side length. We have 3 times 3 squared times ds dt. So dividing, now we can solve for ds dt. So ds dt is equal to 4 over 27. And the units for that are feet per minute. Okay, so now we have a change in our radius and a change in our cube length. And we have dr dt and ds dt. So now we need to put that together and talk about the change in the total surface area. So I'm going to write down the surface area equations for both shapes. So the surface area of a sphere is 4 pi r squared. And the surface area for a cube is 6 s squared, because there's 6 sides to a cube, and each side is a square. We want to talk about the total change of surface area. So the total change in surface area is equal to the change in the surface area of the sphere with respect to time plus the change in the surface area of the cube with respect to time. So we need to find those two things, fill in what we have, and then combine them. Okay, so we have the change in the surface area with respect to time, and we have to take the derivative now of 4 pi r squared. So that 4 pi can come out front, and then we're taking the derivative of r squared. So since the radius is changing with respect to time, we start off like normal. It's 2 times r, but then we have to plug in dr dt because the radius is changing with respect to time, and we have to use the chain rule. So we have all of this information. So we have 4 pi times 2r, and so that's 2 times 2. And then our change in our radius with respect to time is negative 1 over 4 pi. And so the change in the surface area with respect to time for our sphere is equal to negative 4, and that's square feet per minute. Now, same thing for the surface area of the cube. So take the time derivative of 6s squared, and we'll bring that 6 out front. And when we take the derivative of s squared, we get 2s. But since s is changing with respect to time, we have to include ds dt because we're taking the derivative with respect to time. So now the change in the surface area of the cube with respect to time is equal to 12 times the side length, which is 3, times the change of the length of the cube, which is 4 over 27. So now combining everything, see we get a 3 in the 27, that goes to 9. The 6 has a 3 in it as well, and then I'll take that down to 3. And so we end up getting 2 times 2 times 4, which is 16 over 3 feet squared per minute. The total change in surface area between the sphere and the cube is going to be the change in the cube surface area, because that's positive, because that's growing, minus the change in the area of the sphere. So combining those, that's 16 thirds minus 4. 4 is 12 thirds. So that gives you 4 thirds square feet per minute. And that should do it. That should end the problem. We found the total change in the surface area. And thanks, and I'll see you in the next video.